gonna do a trick. Okay, so I'm gonna prove. So let me do a theorem. So this uses some technology here, and then I'll try and explain what I'm doing here. But I think it's a good introduction to Tor. So if M is finitely generated over a Noetherian local ring, then if M is flat, implies M is free. Okay, we already know that free implies flat. Okay. Okay, so here's the trick. So let me see if I wrote down these properties of Tor that I need. Okay, so the properties. So this uses Tor. So this uses the Tor functor. M dash functors. Okay, and the motto is that Tor measures the failure of flatness. Okay. Okay, and let me kind of tell you what happens. So, okay, so let me just say some things. So, given any exact sequence, so some properties. Okay, so first of all, this is an R module, right? So this will be an R module. So these things here, these are functors from R modules to R modules. Okay, and what are the properties of Tor? Okay, so before getting into it, so first, first property is that Tor I R of M and N is the same thing as Tor I R of N and M. So they're modules and they have this. Two is that M is flat if and only if for all R modules, this first Tor is 0. Okay, and then let me show you what happens. So the third property is that given any exact sequence of R modules. Okay, so let me write an exact sequence down. Right, we get an associated long exact sequence. Okay, and here's how the long exact sequence goes. So what I'm going to do is I'm going to start by doing this. So I'm just going to take the sequence that we had, and I'm going to tensor it up to M. Okay, and so we have we have this right exact part. Okay, the part about tensor, right, is that it's a left adjoint and preserves colimits. So we have this right part, but we don't know that this map is injective. So what happens is that there's this Tor thing, right, that sits here. Tor 1 R, and then we have V prime prime of M. Okay, so notice that if this was 0, this sequence would be exact on the top. Okay, and then we get Tor 1 Vm, and this is Tor over R, and then we have Tor 1 of R V prime M. Okay, and it goes on like this, and it goes on to Tor 2. Okay, and then the sequence keeps going. Okay, and it could potentially go, and you'll have infinitely many Tors. Okay, but what happens is that, so you don't have this exact sequence necessarily, but once you throw in some Tors, it does become exact. Okay, so the image of this is the kernel, and this is kind of a complicated map, this Tor map here. So let me just show that. So let me show that 3 implies 2, just real quick. Let's see, actually, yeah, 3 implies 2. Let's do 3 implies. Okay, well, let me show something like, okay, let me give like an example. Or I don't know what to call it. Let me just call it a lemma. Assuming 3. Assume 3. If Tor 1 Rm n is equal to 0 for all n. Let's do it like this. And I'll assume commutativity too. So well, actually, I don't need to. Let's do it like this. If this is 0 for all R modules, then M is flat. Okay, so the proof is exactly what I said before. Okay, so if so you do this is exact, right? Then what you do is you tensor. I'm just kind of repeating what I already said here, but let me just make it explicit, I guess. So we have this exact sequence, Tor 1, V prime prime, M. This goes into V prime tensor M over R, V tensor over R with M, V prime prime tensor over R with M, and then this goes to 0. Okay, and so this thing is equal to 0 by hypothesis. Okay, and so since we showed this for any exact sequence, right, then that shows that tensoring up is exact, which shows that that's the definition of n being flat. Okay. All right. So now let me go and prove the result. Okay, assuming these properties of Tor. Okay, so the proof. Okay, so the proof that that flat implies free under the hypothesis. So, okay. So here's what we'll do. Okay, so we're gonna do, so again, we're gonna let M, so M is gonna be finitely generated over R. R is a local ring. And R mod M is going to be, we're going to call that K. Okay, so M bar here, this is M mod the maximal ideal times M. So this is a finite dimensional K vector space with generators x1 bar, x2 bar, we could go to xn bar. Okay, so by Nakayama, so these lift to generators of R, or generators of M, sorry. Okay, so we have this r to the n. It goes like here. We have the surjective map phi. It goes like this. Okay, and so this map here is phi of ei. So this is the standard basis vector. Goes to xi. All right. So by Noetherianity. So this is the exact setup that we had before in the previous theorem, where we showed that projective implied free over a local ring. So Noetherianity, the kernel is finitely generated. Is finitely generated, giving an exact sequence here. So 0. So we have the kernel of phi, r to the n, m like this, phi, and we have 0. Okay, so we have an exact sequence. M is finitely generated, and the kernel is finitely generated. Okay, so now we're going to use the property of, we're going to tensor up to k. So now we're going to apply the functor here, r with k, and use the long exact sequence, the Tor long exact sequence. So here, notice that I'm tensoring. We're using. Okay, so this is kind of weird, right? So I want to point this out. So here we're trying to show that we have that m is flat, okay? But we're not tensoring up with m. We're tensoring up with k, okay? So what we're doing is right. So what do we get? So we get this m tensor k. Okay, we have here r to the n tensor over r with k. We have the kernel of phi. So this is, let me move it over. Kernel of phi, tensor over r with k. Okay, and now we're going to use the long exact sequence here. And what do we have? We have Tor 1 m or r. So it's the r version of Tor for r modules. R, and then we have m k. Okay, and if we were to continue this just for the sake, we only need this part here, but just for to continue, like, so we have Tor 1 r to the n k. Okay, and then we have, etc. Okay, so we're doing the Tor thing, and it has k's everywhere. Okay, but that doesn't matter because this thing is 0, right? So this thing here is equal to Tor 1 r, km. And this thing is 0, right? Because it was 0 for every R module, right? So that means that this sequence is exact. Okay, so this implies that we have here, so we have the kernel. So we get an exact sequence. So this is 0. So this was the Tor term, that 0 term there. R with k. And this goes to so this goes to m bar. Okay, so this thing here is just k to the n as well. And this was a k to the n dimensional vector space. Okay, so so this map is surjective. So by the dimension theorem, so which says that the rank of the map plus the nullity of the map, right? I mean, this was cooked up exactly so that this is an isomorphism, right? So this thing has to be 0, right? Rank plus nullity is dimension. So the nullity needs to be 0. So this kernel is 0-dimensional, right? So the 0-dimensional K vector space is the 0 vector space. So this implies that the kernel of phi tensor over R with K is 0. Okay, and again, I'm going to remind you that this is the kernel of phi tensor over R with R mod MR, right? And this thing here, what is this? So this is the kernel of phi. So maybe I should be putting isomorphisms everywhere. So this is this mod this, okay, multiplied by M, okay? And so this tells us that the kernel of phi is equal to the kernel, let's see, M times the kernel. So I'm just going to write left and right multiplication as the same, okay? And so this implies that, so this is by Nakayama, right, that the kernel of phi is 0. And so a key part of this, right, in order to apply this, the kernel needs to be finitely generated, okay? So just kind of a remark. In order to apply this, need this kernel here finitely generated. Okay, so what do we have? So we have the kernel of phi is 0. So let's go back to our sequence here. So what does this tell us? So the kernel of phi is 0. That is here, right? So we go back. This thing here was 0. Okay, so this tells us that M is free. Okay, M is isomorphic to, R to the N. And so what did we prove? We proved that flat implies free. Okay, under those finiteness hypotheses. Okay, so so the corollary of this one is that flat modules are locally free. So if M is finitely generated over a local ring, a local Noetherian ring, then M flat implies M is locally free. So flatness and locally free are under finiteness hypotheses are the same thing, essentially, because we already showed that locally free implied flat. Okay, and so that gives the result that we wanted. So I guess what I owe you is a little bit about Tor and what that's all about. Okay, so I'm going to stop the video here.